Hello, I'm John Doherty. The subject of this video is structural overlay parameters. Structural overlay parameters are implemented in a utility program called PLPROC, which is provided with the PES suite. PLPROC is normally run as a simulator preprocessor in the model batch or script file, which is run by PEST or PEST++ as a model is undergoing history matching. Simulator post-processors will normally include programs which undertake tasks such as spatial and/or temporal interpolation from simulator outputs to the times at which field measurements were made. PLPROC, however, takes care of parameterization duties. A lot of PLPROC functionality is focused on pilot points, but it also supports other types of parameterization, including structural overlay parameters, which are the subject of this video. PLPROC comes with a comprehensive user manual. Because it's quite complex, because the tasks that PLPROC can perform are quite complex, various aspects of its functionality are available through function calls. So PLPROC has its own language, and the contents of a script file can be very long if the parameterization of one's model is complex, as it often needs to be. The functionality that it offers and the different ways that it can offer that functionality are all user adjustable. PLPROC, like PEST, is model independent. It can work with models that have structured or unstructured grids. For this video, our attention falls on 4 of its functions, which are listed in this table, and these functions pertain to structural overlay parameters. Now, in talking about structural overlay parameters, we're actually talking about features that are superimposed on an existing model grid. So for demonstration purposes, here's a model grid. This grid has 100 cells in each direction, and each of these cells is 10 meters by 10 meters. Superimposed on this grid are 2 features for demonstration purposes. The first of these features is a polylinear feature. We can have a number of these features, but we're just having 2 for demonstration purposes. The first feature, as I just said, is polylinear, and as such it could represent a fault, an alluvial channel, something like that. The second feature is a polygon. It could represent, for example, a hole in an aquitard. And for purposes of illustration, we'll assume that the background hydraulic conductivity of this layer is 1 meters per day. So these features are going to be superimposed on this model layer. They could be superimposed on multiple layers, but we're just looking at one layer in this example. Now, the hydraulic properties that are associated with features are assigned to their vertices. In this case, I'm assigning hydraulic conductivities of 10, 20, 30, 40 meters and 50 meters a day to the vertices of this polylinear feature. Similarly, I'm assigning hydraulic conductivities of 10 to 50 meters a day to the vertices of this polygonal feature. Now, I can assign hydraulic properties to the features, but ultimately what I have to do is assign hydraulic properties to the cells of the model grid. The model doesn't know anything about features, it only knows about cells. So we have to take these properties and superimpose them on the cells of the model grid. Now, this superimposition process is actually undertaken in 2 steps. For a polylinear feature, The first step is linear interpolation of hydraulic properties down the linear feature. So at any point along the feature, the hydraulic property is a linear interpolation between vertices on either side of that point. Slightly different for a polygonal feature, the first step is aerial interpolation from the vertices internally to the feature. Aerial interpolation takes place using inverse power of distance. The user selects the power. The next step is to go from the feature to the underlying model grid. So to explain this, let's take a section through this polylinear feature. Now, if a model cell directly underlies the feature, then it is assigned the same hydraulic property as the point overlying it on the feature. Within a distance W set by the user, the hydraulic property assigned to the model grid is the same as that at the closest point on the feature. Beyond that distance W, the effect of the feature on the background grid decays using a Gaussian function set by a variable A, which is set by the user. So hydraulic properties of the feature kind of diffuse away from the feature to the model grid in a continuous fashion, with the user determining the diffusion distance. A similar process operates for a polygonal feature. Here, inside the polygon, however, hydraulic properties which are linearly interpolated from polygon vertices are dumped directly onto the underlying model grid. Away from the boundary of the polygon, we have this diffusion process again. Within a distance W of the polygon boundary, the hydraulic property assigned to the model cell is the same as that at the closest point on the boundary. And then the influence of the polygon on the underlying model grid decays rapidly with a Gaussian function with the decay rate set by the user using this variable A. Now, as I said a moment ago, how the underlying grid is populated with hydraulic properties does not affect this diffusion process. Regardless of whether the underlying grid is populated with random parameters or with hydraulic properties interpolated from pilot points, the diffusion process takes place from the feature to the background properties that already exist in the grid, regardless of the heterogeneity of those background properties. So let's have a look at this in action. Recall that we've assigned a background hydraulic conductivity of 1.0 to the model grid, 10 to 50 to vertices of the linear feature, 10 to 50 to vertices of the polygonal feature. Now, if W is 10 and A is 10, then the effect of the feature on the underlying grid is restricted to the immediate vicinity of the feature itself. However, for larger values of W and A, the effect of the feature on the underlying model grid is much more widespread. Here we illustrate the fact that both W and A, like the hydraulic properties assigned to the features themselves, can be variable. Individual W and A values can be assigned to individual vertices of each of these features. And that's what's illustrated in this picture. So you may ask, why do this? Why have a diffusion process from the features to the model grid? Why not just plonk the features on the grid and have a sharp boundary between properties under the feature and properties on the model grid which are not under the feature? Well, the reason is, as we'll discuss in just a moment, we want to have the ability to adjust the location of this feature. And when we do, we want the relationships between model outputs and location of the feature to be differentiable. We want the location, the position, the shape of these features to be history match adjustable. And this requires that the relationship between their locations and their properties and model outputs that are used in history matching be continuous. And this mode of transfer of properties from the feature to the model grid ensures continuity of model outputs with respect to feature locations as these feature locations are moved during history matching. So that's the reason for these gradual change, user adjustable but gradual diffusional process where we move from the properties of the features to the properties of the background grid. So let's now have a look at details of how these features can move. To move these features, we place their vertices on sliders. So each vertex of this polyline is now attached to another polyline along which that vertex can slide. The position of that vertex on the slider is governed by a variable which I'm going to call pos. This is user assignable variable called pos, which can vary between 0 and 1. If pos is set to 0, then the vertex is at the beginning of the slider. If pos is set to 1, then the vertex is at the end of the slider. The same applies, of course, to the polygon. So let's see how this works. Here I'm interpolating or diffusing properties from the features to the model grid with W set to 20 meters, A set to 20 meters and pos set to 0 for all vertices of both of these features. So all vertices are at one end of their respective sliders. Here, pos is set to 50 at all vertices. Here, pos is set to 1. And here we have random pos. Now, and also, not only is pos random, but A and W are random in this picture. Now let's get just a little more sophisticated. Now I'm going to move the entire feature. So to do that, and we'll just concentrate on the polygon to demonstrate this aspect of structural overlay parameter functionality. I'm introducing a global slider, and I'm attaching this vertex of this local slider to the global slider. And as this vertex slides along the global slider, so too will the entire polygon. I'm introducing a new variable called global pos. Global pos can vary between 0 and 1. If global pos is 0, then this vertex is at the beginning of the global slider. If global pos is 1, then this vertex is at the end of the global slider. So let's demonstrate this. Here, W and A are set to 30 meters. Pos is set to 0.5 for each vertex of each feature. So each of these vertices is halfway along its respective slider. Global pos which dictates the location of this polygon, is set to 0, and here is this local slider sitting right at the beginning of the global slider. If global pos is set to 0.5, the polygon is moved halfway along the global slider, and if global pos is set to 1, then the polygon is moved to the end of the global slider. And here we have random values for W, A, pos at each of the vertices, and the whole pos, which dictates where the polygon sits along the global slider. So you can see there is an awful lot of user adjustableness about the locations of these features. Not only can we assign hydraulic properties to the vertices of these features, we can assign these vertices to a position along a slider dedicated to each vertex, and we can slide the feature as a whole along a global slider. So that covers the functionality available through structural overlay parameters. So the next question is, where can we use this functionality? What are some of the places where this may be useful in decision support roles that are performed through modelling? The first use to which structural overlay parameters can be put has actually already been done and is documented in a GMDSI worked example. Now, what was actually used in this worked example is not exactly structural overlay parameters as I've just discussed here, but the predecessor to structural overlay parameters. What was done here could be implemented using structural overlay parameters a little bit more efficiently and easily than was done in this worked example. This model was built to look at inflow into a tunnel. And inflow into the tunnel was likely to be greatest where their faults intersected the tunnel, the trajectory of the tunnel. So the locations of the faults were known, or roughly known. They were parameterized using polylinear features, so with hydraulic properties assigned to vertices of these features. The hydraulic properties were then mapped to 19 of the 20 layers of a model grid. They weren't mapped to regolith because regolith happened after the faults. And we can see the outcome of this mapping process in this picture in front of us. The width, the diffusion width, which takes hydraulic properties from the faults to the model grid, was set wide enough so that there was continuity of flow along these features, even though they did not coincide with the directions of model rows and columns. That way, flow could take place around these bends with a little extra diffusion in order to allow perhaps to accommodate damage zones around the faults. So insertion of these faults into the model domain and transferring of the properties of these faults from the features to the model grid took place pretty much as we've just described, and made insertion of these faults into the model domain quite easy. Another potential use actually arises, this is hypothetical, but it arises from experiences that I've had in the past where I wish I had something like structural overlay parameters at my disposal. So stories like what I'm about to tell you were part of the reason why I put structural overlay parameters into PLPROC. Suppose we have a tailings dam and we've got boreholes around the dam and heads are measured in these boreholes. Suppose that some of these water levels suggest that there may be leakage of water under the dam. Can we use modelling to test whether this may actually be happening? Are the water levels that we're observing in these wells consistent with leakage under the dam, possibly through structural features which are known to exist, but their exact locations are unknown and their ability to conduct water is unknown? Can we undertake modelling as inquiry to see whether what we're observing is consistent or inconsistent with the movement of water along structural features under the dam? So we may build a 1 or 2 layer model, populate those layers in ways we normally do, for example with pilot points, and then introduce structural overlay parameters to represent the effect that a fault whose location and properties we don't exactly know may have on flow of water in the vicinity of the dam. We can then calibrate this model using PEST or PEST++, ask for a good fit with heads that are suggesting to us that there's something going on here, and ask PEST to find a location, if it can, and properties for a fault that could explain heads that are being observed in these wells. So we're giving PEST the possibility and inviting PEST to parameterize a model in a way that may explain what we're observing in these heads. Now, if PEST cannot find a location and properties for the fault that will explain those heads, we can reject the hypothesis that flow through highly conductive, narrow connected material is causing those heads. But meanwhile, by parameterizing the model in this way, we are giving PEST every opportunity to explain what is being observed in the field, and which may have important consequences. The final example is also hypothetical. However, it's kind of common day decision support modelling, and certainly reflects some of the experiences that I've had, and I've wished that I've had better parameterization tools at my disposal. Suppose that someone wants to put a mine at this location, and they ask, is this mine going to have any impact on this river? And perhaps one of the possible impact pathways is that pressure reduction will travel along this conductive seam, like a coal seam, and let's assume that the aquifer next to it is reasonably hydraulic conductive, but there's an aquitard here which could perhaps shield the river from impact, or not, depending on what happens because of this fault, whose position is roughly known, but whose length is not really known, and certainly whether it offsets that aquitard by enough to formulate to create a linkage between these two aquifers is not exactly known. Nevertheless, our task in assessing the possibility of impact is to ask, is impact possible? Let's assume that we have some data available. We have pumping in these red wells and heads observed in the blue wells, so we have some information about the hydraulic properties of this system. Is it enough information to be able to reject the hypothesis that there will be impact? Modelling, it must be tasked to find out if that is our job, is to assess whether there's a possibility of impact on the river by the mine. So the mindset here for decision support modelling is one of hypothesis testing, which after all is the basis for the scientific method. Now, we've talked about direct hypothesis testing using models in other videos, but just a quick refresher. So the first thing we do is we calibrate a model. In doing so, we adjust the model's parameters till model outputs are able to fit measurements of the past. In doing this, we find out a couple of important things. We find out how well we're able to fit the past behaviour of the system. we find out the sorts of parameters that we need to introduce to the model domain to allow that fit. In doing so, we find out the amount of model to measurement misfit that we'll tolerate in our model. We'll find out how many bumps and lumps we're willing to tolerate in the parameter field. Model to measurement misfit is often an outcome of structural deficiencies of the model. Perhaps some aspects of the parameter field may be because parameters are taking on compensatory roles for model defects. This is inevitable, we have to live with it, and we learn how much we're willing to live with it because no model is perfect. So now we're armed with what we need to go to the next stage of this hypothesis testing process. So now we look at the future. We now recalibrate the model against what happened in the past, but we also include in the calibration data set the hypothesis that we're testing, something we don't want to happen. Most decision support contexts come with a hypothesis, and the hypothesis is something we don't want to happen will happen. In this case, what we don't want to happen is for mining to impact the river. So let's observe that the river is impacted. If I can calibrate this model with the river impacted and still fit the past acceptably well, with a parameter field that I will accept according to the metrics that I learned for acceptability of a parameter field and model to measurement misfit during the preceding calibration process, if I can still fit the unwanted future and still fit the past with an acceptable parameter field, then I cannot reject the hypothesis that what I don't want to happen may happen. So I reject the hypothesis if model to measurement misfit is no longer acceptable and if the fitted parameter field is no longer credible. Both PEST and PEST-HP have modes of behaviour which facilitate this process. So now let's go back to our hypothetical example and let's focus on just the area around the river. Now, we can parameterize the layers of the model with pilot points. But what about that fault? We don't really know the offset of the fault. We don't really know the length of the fault. But we need to represent the presence or possible presence of the fault during the hypothesis testing procedure. If we were to construct a model for each possible offset of the fault and each possible length of the fault, this could become a very difficult procedure. Why not just represent the effect of the fault on the potential of the aquitard to shield the river, and then ask, once we've parameterized the effect of the fault on the aquitard, whether the actual true fault could create that same effect. So I'll show you what I mean. Let's focus on this aquitard. And let's introduce a slider that is in the location of where we think that fault may be into the aquitard. Along that global slider, we introduce local sliders, which allow us to construct a hole in the aquitard which can be equipped with hydraulic properties and can be equipped with a movable shape and movable position. And then we say, PEST, can you please fit the unwanted future, fit what happened in the past, find a place where there could be a hole in the aquitard that will allow mining to impact the river. And if PEST can't find a place and properties for that hole that will allow the river to be impacted, we can reject the hypothesis. Or maybe PEST can find a location, shape and properties for this hole that can allow mining to impact the river. We then ask, can the properties that pest has introduced to this hole in the aquitard be explained by things that a fault can do, by a displacement of the aquitard that it may incur, or by the properties of the fault itself. And if we can explain this by this, then we can't reject the hypothesis that this fault could make or allow the mine to impact the river, in which case, the hypothesis not being rejected, more field characterization studies must be done. In summary then, structural overlay parameters. These are features whose shapes, properties and positions are parameterizable and continuously adjustable by PEST and PEST++. As such, they can be deployed in calibration, uncertainty analysis, modelling as inquiry, and modelling as direct predictive hypothesis testing. Structural overlay parameters are implemented in PLPROC. They can be applied to structured or unstructured grids. And that's it. Thanks for watching.